Welcome. What we're going to do today is take a look at electron configurations, and then we're going to expand those into what's called orbital diagrams. Orbital diagrams are just an extension of electron configurations, and they give us a little bit better picture of what an electron configuration or what the arrangement of electrons actually look like. So let's take an example, oxygen. Oxygen has 8 electrons. Now in these electrons, when I write the electron configuration, I'd write 1s2, 2s2, 2p, 4. Now recall the coefficient represents the energy level, the letter represents the shape of the electron cloud or the shape of the orbital, and the exponent represents how many electrons are in each of those respective clouds. This is an electron configuration. Now what I'm going to do is I'm going to construct an orbital diagram. Here I am drawing an orbital diagram for oxygen. You see 1s, and then you have an up arrow and a down arrow and a little blank. You have a 2s with an up arrow and a down arrow and a little blank. And a 2p with an up arrow, a down arrow, a single up, and a single up in those blanks. This is an orbital diagram. Now you might wonder why the arrangement of those arrows is the way it is. The arrows, like I said, are representing of electrons, but in that 2p, those electrons are separated out. You put one in each blank first, and then you go back in and plug in that second one. Okay, we'll explain why, and we'll explain who tells you why those arrows are the way they are in a few seconds. Recall, this is an orbital diagram. So now what we're going to do is we're going to take a look at where electrons are located. Electrons are located in electron clouds. Those clouds are called orbitals, and any orbital will hold up to 2 electrons. The reason why there's only 2 arrows in that 1s, or there's 2 electrons in that 1s, because there's one electron cloud. It's spherically shaped, and it'll hold up to 2 electrons. In s sublevels, there is one cloud. There is one electron cloud. It is spherically in shape, and it would hold 2 electrons. P's contain 3 clouds, or 3 orbitals. These P's, they're technically called sublevels. They contain 3 clouds. Each could hold 2 electrons. D's, they have 5 clouds, or 5 orbitals, each which could hold 2 electrons. And finally, F's, the F sublevels contain 7 clouds, 7 orbitals, each can hold 2 electrons. And what I'm doing here is I'm drawing an S cloud. Remember, they're spherically in shape, spherical in shape. You can see that they have, one orbital or one cloud. P's, on the other hand, I feel like P's really tell the story. P's exist in 3 dimensions, just like all clouds, but they exist along the X, the Y, and the Z axis. And when I draw in this first orbital is known as the px orbital. It lies along the x-axis. It's balloon-shaped or dumbbell-shaped. This again is known as the px orbital. Along the y-axis, we'd have the py orbital, or py electron cloud. And then along the z-axis, we'd have the pz orbital, or pz electron cloud. Now you can see in the orbital diagram, we're diagramming the orbitals, there are 3 blanks for the p's. The reason why there's 3 blanks is because there's 3 clouds, and 2 electrons can go in each one of those clouds. So like I said, p's really, make sense in my brain. Here I'm going to go ahead and reconstruct the oxygen orbital diagram. We put 2 electrons in each orbital or each cloud. The blanks are what is representing the clouds. So you have 1s with 2 arrows, 2s with 2 arrows. Then 2p, we're going to put 1 electron in each one of those clouds, X, Y, and Z first. So that's going to enable the electrons to get further away from each other. And then we'll go back and we'll plug in that last electron where one of them gets paired up. You'll notice there's a single electron in Py, and there's a single electron in Pz. Down the road, we'll fill those two up. So now what we're going to do is we're going to go ahead and see why we fill up those orbitals in the manner in which we do. You can see that we filled up the 1s first, followed by the 2s, and then in the end we put electrons in the 2p. Well, here we have Aufbau's principle, Hund's rule, and Pauli exclusion principle. Aufbau's principle says electrons occupy orbitals of the lowest energy first. What that means is what that tells us is that we should put electrons in the 1s before we put electrons in the 2s, because the 2s is at a higher energy state. That is, they're further away from the nucleus. When we look at Hund's rule, it says electrons occupy each orbital in a sublevel before a second can be added. And that is really demonstrated in the 2p's, where we put 1 in each blank first, 1 in each cloud first, so that they get as far away from each other as possible, and then go back and then plug in the second. And last but not least, Pauli exclusion principle says that basically electrons need to have opposite spin. Right? And when we're putting electrons in, you'll see that one of them has an up arrow, the other has a down arrow. Those arrows are representative of the spin of each electron. The reason why, there are the underlying principles for each of those 3 rules, is electrons are attracted to the nucleus. The nucleus is positively charged, electrons are negatively charged, and so there's an attraction there. That is the underlying principle behind Aufbau's principle, where they've got to occupy the lowest energy first. When it says that electrons are repelled by other electrons, that is when you can see in the 2p's, we'll plug 1 in each first. That repulsion allows electrons to get further away from each other. And finally, stability is created from balance, and that's where you can see we don't put 2 arrows in the same direction. We put 1 up, followed by 1 down arrow. And that cancellation of spin allows for that orbital, or that electron cloud, to become more stable. In the 2p's, again, electrons are repelled, we spread them out, and then we go back and then plug in that 4th electron in the 2p's, making oxygen have 8 total electrons. Now briefly we'll look and reflect on electron configurations. The coefficient tells us the energy level. The letter tells us the shape of the electron clouds or orbitals, and the exponents represent the numbers of electrons. Orbital diagrams are no different. Now what we'll do is we'll show you that there is no difference between an electron configuration and an orbital diagram. Let's take this first example of aluminum. Aluminum has 13 electrons. Its symbol is Al, and its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p1. This is the electron configuration for aluminum. The exponents here are representative of the numbers of electrons, where 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 1 is 13. 13 electrons. When I draw and construct the orbital diagram, I construct it very similar to that electron configuration. I start at the 1s, plug in 2 electrons. Jump to 2s, plug in 2 electrons. Move on to 2p, plug in 1 electron in each orbital first, and then go back in and plug in the second one. In the 3s, I draw in my orbital, my blank, representing my electron cloud, plug in 2 electrons. Move on to 3p, draw in 3 blanks, because we got the px, the py, and the pz. And then here I plug in my 1 single electron in the 3p, where I finished with 13 electrons for aluminum. So now let's take a look at a larger element such as copper. Copper has 29 electrons. Copper is located in the D block on the periodic table, so we're going to have electrons in the S, the P, and the D blocks, where our electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 9. This is the electron configuration of copper. You can see here on the periodic table, copper located right over my mouse, element number 29 in the D block, second to last element. Now what we'll do is we'll construct the orbital diagram. Just like in aluminum, we start with 1s and plug in 2 electrons, followed by the 2s, electrons represented by up and down arrows. 2p, 3 orbitals, 3 clouds, px, py, and pz. Spread them out by putting 1 in each first. Next, 3s, 2 electrons, 3p, 6 electrons will go in here. We spread them out first, and then we go back and plug in the second, and the spins will cancel. That provides stability. Next, I'm going to jump down and leave a little bit of space for my 3D so I can group my energy levels together. I'll plug in my 4s electrons, and finally, last but not least, let's plug in our 3D. Remember, Ds have 5 orbitals, or 5 electron clouds. It's still similar, where each will hold 2 electrons, we just have more clouds. It's bigger. We'll plug 1 in each first, and then go back in and plug in the second electrons. As many as we need. We need 9 3D electrons in this case. This is the orbital diagram for copper. Recall when we have the S block, the S contains 1 orbital, it's 2 elements wide, and there can be 2 electrons. P's have 3 orbitals, and they can hold 2 electrons each. The P's with its 3 orbitals and 2 electrons is 6 elements wide. The D's is 10 elements wide. It contains 5 orbitals. Each orbital, each cloud can hold 2 electrons. That's how it is capable of holding all 10 electrons. And then our F's, 14 elements wide, 7 orbitals, 7 clouds, each holding 2. 7 times 2 is 14. Those clouds will hold 14 electrons. Remember, those electron configurations are very similar to orbital diagrams. What you should do is do the electron configuration first and then the orbital diagram. Here is a set of questions for you. I would like you to now go in and complete each of these items